All right, so I have pretty much everything the way I want it. dp, so dp would be equal to k over 10 minus t dt. Integrate both sides, and you get p equals, well, I would, hazard a guess that it's a natural log of 10 minus t, but what would be the derivative of the natural log of 10 minus t? All right, it's Monday. It would be negative, right? Okay, so I need it to be positive, so let me negate my integral. All right, so the plus c comes from the fact that I'm integrating, and there we have it, because it's solved for the value of p, which is my independent variable, in terms of the variable t, so we're in good shape. This question's not asking us to figure out the values of the constants. It didn't give us any conditions associated with it, so we'd be done at this point. I mean, if you wanted to make the negative k an exponent, you're welcome to do that. It doesn't really advance the cause, though, without any context. Right?
Why did you make the k negative?
Because the derivative of the natural log of 10 minus t is negative 1 over 10 minus t, and we have a positive. All right, so then we get into some, basic verbal statements, nothing too crazy. Solve the differential equation that models the verbal statement. Rate of change of p with respect to t is proportional to 25 minus t. So in that case, it says proportional. It doesn't say directly, inversely, or jointly. It's implied that it's directly. All right, when we say something is proportional, we're saying that it is directly proportional. It's when we attach another word to it, that's when we're moving it into a different category. All right, so the rate of change of p with respect to time, I'm assuming time, dp dt, means equals, proportional, which means it follows the model y equals kx. All right, so this is the model from way back in Algebra 2. That's the model we're following, y equals kx. So dp dt takes the place of y. K is the proportionality constant. I've been using that term a lot without ever really explaining what it was until today. Proportional to 25 minus t. All right, so that's taking on the role of x. So you could see that dp dt equals k times 25 minus t is taking on the same form as y equals kx. Something equals a constant times something else in terms of a variable. All right, so our only job at this point would be to integrate both sides, solve for the value of p, or solve for p in terms of t. All right, so very close to being a separated variable situation. So dp is equal to k times 25 minus t dt. Integrate both sides. P is equal to, I'm going to write it as k times the antiderivative of 25 minus t dt. And what is the antiderivative of 25 minus t dt? Minus a half t squared, or 25t minus t squared over 2, as I heard someone say. All right. Plus the c. All right. So we want to make sure we put the plus c in anytime you're finding the antiderivative. All right. And when you're solving differential equation, you're taking the antiderivative, so you got to have the plus c. All right. As some of us learned on those one of those mini quizzes. Sometimes you don't need the plus c, because if one of the rules does not have you actually taking an antiderivative, there is no plus c to be had. All right. The rate of change of y with respect to x varies jointly. All right, so joint variation, we have the model above, y equals kxy. All right, you can write it as f of x comma y if you want to be fancy, but it's a function, not y, z, 3 variables. But f of x comma y does the same thing. So you could say, in your mind anyway, something equals a constant times 2 other variables. all right, or expressions related to two other variables. So y with respect to x, the rate of change, dy dx, varies jointly. So we have a proportionality constant k as x and L minus y. All right. Joint variation really applies. Well, I mean, there's contextual applications of it, because anytime you have multiple variables within a situation, it would make sense. You know, like if you're talking about volume produced over time, with the variables being not only time, but also temperature. You know, so you think about weather considerations, well, a bunch of variables that go into weather predictions. So, you know, these applications would fall into that category. But also geometrically, it would fall into 3 dimensions rather than just 2 dimensions. Right? But anyway, I can separate variables. Y's go to the left, x's go to the right. Because it's a function of 2 variables, it's not that bad. The L takes on the role of a constant. All right, so 1 over L minus y is equal to, dy is equal to kx dx. Integrate. All right, so I need the antiderivative of 1 over L minus y. Again, assuming L is a constant. It's pretty much the same as the first problem. So negative ln absolute L minus y is equal to antiderivative of kx. So k over 2 squared plus c. All right. Now we could go to the distance here and solve, and it's good practice to do so. The question isn't really calling for it, but I'll do it anyway. Can negate both sides. Keep that natural log clean. Exponential form. That constant can be broken off and made into the coefficient. And when that happens, the L minus y is freed from the absolute values. And then the final step would be just to get y alone, which may be broken into more than one step. But if I subtract L from both sides and then negate both sides, bless you. We'd be looking at something like that. Right? Because the C, when you negate it, it's just going to remain as C. But when I subtract off the L, it becomes negative, but then I negate it, it becomes positive. All right, so this one, I think the more work came in the actual cleanup process than doing anything more than that, you know, in terms of setup. After that, it's just another differential equation for some reason. I don't know why this problem is here. Oh, yeah, it's, okay. Yeah, it probably should be moved to a more appropriate place.
I thought it was a trick question for some reason.
Maybe it was somewhere along the lines, it was like a confidence booster.
Yeah.
After that one, it's like, all right, let's just make sure people do understand that they do know some calculus. So, okay, do that one. Yeah, okay, I know some stuff. All right.
Why do you keep pulling that up? I was scared.
All right, because number 4 was well, maybe it was a compare and contrast. I don't know what I was thinking, but number 4, this is an important one because we could rewrite it as 1 over 4 minus y is equal to just a 1 dx. I mean, you don't have to write the 1 anymore if you don't want to, but the reason I like to go over a problem like this one is to remind you that sometimes a differential equation will naturally solve itself in terms of one variable as opposed to the other. All right, so here we're looking at x on the right-hand side, just an x. On the left-hand side, I mean, we've done this a few times already now, so this would be negative ln 4 minus y. But you may opt, and so may the College Board, to put your plus c over here. Because remember, going way back to like the beginning of this unit, packet, I guess, we talked about the idea that you could put the plus c on one side, both sides, didn't matter. So then the question became, well, okay, we'll just put, well, it wasn't even a question, it was just like we decided, let's just put it on the right-hand side, because if we're going to solve for y anyway, wouldn't that make the most sense? But some equations naturally solve themselves for x. You know, they become the sideways variation. You know, that's oversimplification. It's really the inverse relationship. Right? So I can easily, well, not easily, like a step above easily, put this in exponential form and solve for y in terms of x. But 1, I don't know that I need to do it. 2, I don't know if I want to do it. And then 3 is like some combination of those two things where maybe I don't need to, maybe I need to do it, but maybe I don't have to go all the way. Because maybe the choices on the multiple choice part of the exam is some hybrid of the two answers, right? So, you know, like, what did he say? A good king doesn't go looking for war, or battle, but must always be ready for it. That's the reference, right? Movie?
I don't know. But it's just like one of those things that just exists.
It exists, but it also exists in the Marvel Cinematic Universe.
Oh, really? Oh, it's
Gotta be related to a king.
It's Thor's dad.
Yeah, it was Odin.
Yeah.
It's the worst day.
Do I get extra credit for that?
No. I mean, if I didn't have to guide you to it so much, I mean,
Yeah.
the roadmap I had to draw to get you there, if that didn't have to happen, then maybe. But, and honestly, I'm just kidding because I don't think I'm allowed to give you math bonus points for Marvel trivia. Yeah.
But if it relates somewhat to math, would you like the trivia?
And it turns into a presentation involving Thanos and population control. Then we can talk.
The population group after.
Yes, right.
That was probably the best presentation I've ever made. Ever.
When you're invested in it, it tends to go a little bit further.
No, actually, I'm really interested in
Yeah, yeah. I mean,
Yeah.
like really invested, not like getting points in math class invested.
Yeah, it was interesting.
I had a good time doing it.
Yeah. I enjoyed it.
No, I don't know.
Oh, speaking of population. So, yeah, this problem, it's a good problem. I don't want to sell it short. It's not fun. No, it's fun. It's fun. It's math fun.
It's not to be fun now.
It takes a few lines of space to complete. I'll stop with the preamble. Let P of t represent the number of wolves in a population at time t years when t is greater than or equal to 0. Probably the t didn't need to be defined, but you never know. There is context that allows for t to be negative, so it never hurts. The population P of t is increasing at a rate directly proportional to 800 minus P of t. All right, increasing at a rate directly proportional to it. All right, so what we would say is that dp dt That I get that. Yeah. dp dt at a rate directly proportional. So k is going to follow y equals kx, proportional to this model. 800 minus, instead of writing p of t, I'm just going to write p, just for brevity. So I have to solve this differential equation. Now they give us some conditions, and we'll handle those conditions. But this goes back to, I think it was like page 3 of the packet. This is page 34. So it's paying off something I said a while ago. We did a problem, I think it was bacteria growth, it was population. It had that entire preamble there. It said words to the effect, it might have even said almost exactly the same words. Population is increasing at a rate directly proportional to demand. And then right after that, it gave you the function. And in that moment, I said, all right, in a few weeks, you got to understand, at some point, you're going to have to come up with these functions yourself, these models yourself. Right? We're here now. Right? This is that moment. Very exciting. So once we have the model, though, we do what we have always done, solve the differential equation. So 1 over 800 minus p dp is equal to k dt. All right, antiderivative of 1 over 800 minus p. And right-hand side is just kt plus c. Now, we have conditions here to work with. When that happens, it tends to be the case that we would want to clean it up. Also, we eventually have to find a limit from this, and the limit is related to the function p. So I need to solve this for p in terms of t. All right. So just like I think it was the joint variation problem that we did on the previous page, I'm going to negate both sides. I'm going to convert to exponential form. I'm going to release the c from its captivity. And when that happens, the 800 minus p will be released from its captivity. Again, because the c will absorb the plus or minuses that come from the absolute value. Question?
Yeah, when you're gonna isolate p and you have negative ce to negative kt, can you bring down that negative and make it positive?
Bring down the negative and make it positive.
Like the negative kt, bring down the negative.
Now you're stuck with that. All right. So now I want to solve for p. So I'm going to swing over the 800 and negate both sides. So we're looking at p equals, the c is going to remain unchanged. The negative 800, after I subtract it over, it becomes negative 800. I'm going to negate that again. It's going to become positive 800. All right. So we have the solution to the differential equation, which is wonderful. I need to find not only k, but I also have to find c. All right, so we have two constants. I need two conditions. In part A, they give me the first condition. In part B, they give me the second one. So that's great news. It also means we have to do the work, which is not so great news, but it's news. All right, so p of 0 equals 500. So 500 is equal to CE to the negative K times 0. I'll make that blue. Plus 800. From that, we can get the value of C, which is what? 300. All right, and we know that because anything to the 0th power is 1. So this E part of it is canceling out. So this would become C plus 800 is equal to 500, C would have to be 300 in order for that to be a true sentence. All right. So I have the C value. That's good news.
Wait,
Would it be
negative? Would it be
Negative 300,
Yeah.
as I said. All right. And a quick check would be just to replace your t with a 0, just make sure that it comes out to equal 500. All right. But that's akin, bless you, to just checking your work in the previous step anyway. All right. Next up is to figure out the value of k. P of 2 is equal to 700. All right, so we're going to have 700 is equal to negative 300 e to the negative k times 2 plus 800. All right, so I took my better equation, I guess. Negative 300e to the negative kt plus 800. And replace the t with a 2. Replace the p with a 700. Now I have to clean that up. But not much to do. I could subtract the 800. All right? As much mental steps as you can do is preferred. Because at some point you got to be thinking time. So e to the negative 2k is what I'm looking to get alone. And we'll worry about what that amounts to in a couple of minutes. I'm subtracting 800 from 700. What does that give me? Negative 100. I'm going to divide negative 100 by negative 300. What does that give me? 1/3. All right, so. Yeah, and the reason why I'm pointing it out this way is because you've got to understand on the AP, that you look at this now and you say, well, no way this is on the non-calculator part. It could totally be on the non-calculator part. I mean, it's very doable by hand, and especially when you see how, what comes with it. Right? I could solve for k still without using a calculator. I can convert to log form 2 ways, by using the conversion log or dan, or just taking the natural log of both sides. Either way. I find that people like doing that more, so that's what I'll do. So we'd have negative 2k is equal to natural log of 1/3, making k equal to negative 1/2 ln of 1/3. If you want to consolidate it into a single natural log without a coefficient, you could write it as ln of 1/3 to the negative 1/2. But then you might look at that and say, well, that's not much nicer. What does a negative sign do to the base of an exponential? You raise something to a negative exponent, what happens to a number? 1 over. You take the reciprocal. All right, so this could be also thought of as ln of 3 to the 1/2, or more concisely, ln the square root of 3. All right. Which one is the best? I don't know. We'll see in the next steps. All right. But if you really look at where we started and where we have to end up, obviously, the simpler k that we plug into our equation, the better off we're going to be. I mean, that's a pretty safe bet. Because eventually we'll have to do a substitution, all right? So, a substitution. We have to find a limit, which might involve some substitutions. But we have a value here for k, which I can then plug in, all right? So, we could take a look at the different possibilities here. So again, p is equal to negative 300. E, I'm gonna write the whole thing out, negative kt plus 800. We now know what k is equal to. What I want to do is choose the most really advantageous thing to plug in. And really, in the end, I don't know that it necessarily matters too much. Looking at our different possibilities, you might say maybe go for this one, but you would have an issue because there's a t there, right? So if I replace the k with a natural log of 3, and the reason why I would say this one is because it's the simplest one, but also I want to get to a point where I can actually use the fact that I have an e and a natural log to my advantage, meaning the e and the natural log would cancel each other out, right? So I want to have the simplest form involving a natural log that would allow that to happen, right? So out of these three possibilities, I might consider going with the black one or the red one because of the fact that there is a t there, all right? I might even consider going with the black one, and well, might even consider, that's the one I'm going to go with because I have a negative value there. That's going to allow me to clean it up even further because the negative would offset the negative that was there to begin with. So I'd have negative 300 e to the negative, instead of kt, I'm going to write t, and then I'll put my k there of ln 1/3 to the negative 3/2 plus 800. 1/2. Yikes. That's a Monday morning. All right, because that's going to allow me to consolidate these two things, put them together, and come up with p equal to negative 300 something plus 800. If I bring the negative t up and multiply it with the 1/2, it's going to become negative t over 2, right? So I'll have natural log of 1/3 t to the t over 2 power, but it's e to the natural log, which is going to cancel out. So it would just be 1/3 to the t over 2 power. And that would be my function. Now you can get it a bunch of different, if you got to this point here and plugged that in there, you would have cleaned it up, it would have given you the same thing. But you would have to know to use your log rules, all right? And that's the thing that people lose sight of fairly frequently, especially when a calculator is involved, because you get to this point here and all of a sudden it becomes a decimal, go through the rest of the process, get wonderful decimal answers that are all equivalent to the correct answer. The only problem is the multiple choices don't have any of those. And so now you have to diagnose which of the choices is equivalent to the one that you came up with. All right. So then we get to this, and you say, all right, well, it's a clean, concise answer, which, if I had something with disgusting decimals all over the place, and then I get to part C where it's asking me to find a limit, which one am I going to be more inclined to work with, Probably the one that's cleaner. Speaking of which, I need to find the limit as t approaches infinity. Of that function. All right, so this is my part C. All that stuff above was parts A and B, all kind of mixed together. Again, without using a calculator. So I got a plus sign. That's good news. What is the limit of a constant equal to? A constant itself. So this one's going to be 800 no matter how you slice it. All right. Now, the reality is you need to come up with an answer here. It should be the correct one, ideally. There is no penalty for knowing the limit in your head unless you're asked to find the limit using a particular approach. In this case, you could use you use a bunch of different ways. You use the squeeze theorem. You could use L'Hopital's rule. You could use a numerical method. You could actually just plug some numbers in. But you could also use common sense. All right? You have a fraction. What happens when you raise a fraction to a very large power? It gets very, very small and approaches what? 0. All right? So you could also apply common sense instead of doing all that stuff and realize that that's going to 0, and therefore the result should be equal to 0. All right. That happens to be known as a geometric relationship, but that's not really within the scope of the course. It's more like any kind of exponential function. As you know, it increases without bound if your base value is bigger than 1. If it has a base value that's between 0 and 1, it's going to 0, assuming you don't have a y-intercept other than 1. So that's all that stuff that you did in Algebra 1, Algebra 2, where you're like, oh, let's look at the different asymptotes, the end behavior, and all that stuff. You're like, what is this ever going to be used for? It's so that you can do limits in your head. That's really what it's all about. I think in 3 weeks we're going to get to that in Algebra 1, and so their payoff for that is going to be today, 4 years later. Like that kind of sucks. But wow. But that's what it is. It's like, what happens when you have a base value of 10? What happens when you have a base value of 2? What happens when it's e? What happens when it's negative? What happens when it's a tiny fraction? What happens when it's a large fraction? All these different possibilities where you're like, all right, enough, we get it. Can we just put it in the calculator? And then you're sitting here in this class in the moment where it's like, no, I can't put it in the calculator. I really need to know that information. Right? So worst case scenario, you start making up some numbers. Pop in a 4, for example. Try to keep it clean. Pop in, I wouldn't put a 1 in there. Maybe a 2 gives you a 1/3. Pop in a 4, that gives you 1/9. 1/9 is smaller than 1/3. Right? Pop in a 32, for example. That gives you 16. You can get there. It takes a few minutes, but you can get there. Bottom line is you're going to come up with 1 over something huge, which means very close to 0. Put in something really, really large, you're going to get something that's 1 over getting closer to infinity. 1 over infinity approaches 0. Right? So you could reason it out without actually knowing what the graph looks like. But ideally, you'd make it a point to know what these graphs look like. All right, that's how important this is. Anyway,